Today's kind of a hodgepodge week of sorts. So the original idea was to do a unit on natural language processing, but that's not quite ready. And a really awesome thing happened yesterday, which was that the BIGGAN models were released. So that you're looking at something that was just rendered a second ago. And so I decided to rearrange things just a little bit. And what we're going to do today is actually, I'm going to do a tutorial on GLOW. Some of you who attended the AI lab on Friday, you know what I'm talking about already, but I'm going to show you how to use it now. And I'm also going to show you how to use these amazing BIGGAN pre-trained models that were released literally yesterday. And then we'll do an introduction to this field of music information retrieval, which is kind of the way that I got started in machine learning and also intersects with a lot of the audio deep learning stuff that we've been talking about casually here and there over the last few weeks. And now we'll get a chance to look at it in a little bit more depth. And then we'll do the NLP stuff along with reinforcement learning next week. Not next week, in 2 weeks actually. That's going to be like a sort of super unit, because that's like 2 gigantic topics in one lecture. Obviously they're just going to be introductory, but they'll give you at least a few new tools that you'll have at your disposal. And just a couple of quick announcements. So this, I'm actually leaving tomorrow for about a week and a half. That'll go into Thanksgiving. So we're not going to have class next week, and then we'll meet again after Thanksgiving. And so we'll kind of we'll work out some other things to do for office hours. I think you guys are going to be out like Thursday and Friday at least, if not Wednesday. I don't know how it is here. I guess most of you will be gone Wednesday anyway. So that won't actually be too many days, luckily. And so also that means there will be no AI lab this week or next week. So next week because of Thanksgiving, obviously. This week I'm not here, and neither is Chris. Although, I mean, if anyone is actually interested in taking the ball and kind of organizing it, then that would be awesome. It's like definitely not. That's definitely something that's optional. Please contact me if you're interested in doing that. Also, another announcement, this just came to my attention also a couple days ago. There's this new data set that was released by the Art Institute of Chicago. 50,000 high-resolution paintings. So this is kind of like wiki art, I guess. I don't think it's necessarily like scrape-friendly just yet, but this would be a great thing to kind of get some scraping utility ready for, because obviously it's a gigantic data set. It's really nice, very high resolution, lots of famous paintings. So there's probably a lot that you can do. It also has all the metadata and all that kind of stuff. So there's a lot, definitely a lot here. So just worth being aware of. I haven't looked through it myself, so I can't say too much about it, except that it looks like an awesome resource. I also wanted to show you this because I actually didn't know about this, another thing that just kind of came to my attention. One really nice thing about teaching is that you have to constantly go back on things that you think you know, and then you find all these new things that you weren't aware of. So the Pix-to-Pix next frame stuff that I showed you, I guess it was 2 weeks ago now, showing you how to, like, some of the stuff that Mario had been doing, and also like basically videos like this, which train Pix-to-Pix to do next frame prediction and then run a feedback loop to make video. Magenta actually has what looks like a really nice kind of like utility online for making these. I haven't used it either, but it looks like it's pretty nice and organized. It's TensorFlow, obviously, so worth looking out for if you're interested in trying to generate these. I think it makes it quite nice and easy. So the agenda for today is I'm going to show you guys GLOW, which is really, really cool. How many of you were at AI Lab on Friday? A handful of you, like maybe a third of you. So you already kind of saw what this is all about. For the rest of you, I'm going to review it. And then what we didn't do on Friday, actually, I didn't have any tools ready, but I actually made a notebook that lets us kind of do all the cool things that you can do with it. It's a really, really cool thing. So that'll be the first thing that we do. And then, like I said, yesterday the BIGGAN models were released along on Colab. So I just modified their notebook a little bit to make it easy, really super easy to make interpolation videos. This will be super easy for you guys to do because you don't even have to set up paper space. It's all in Colab. So I'll give you guys the link, and then hopefully we should have a lot of fun with it. And then probably after the break, I'm going to introduce some audio stuff like music, music-oriented deep learning, and this field of music information retrieval, which is also intersects a lot with what we're interested in. Any questions so far? Okay, GLOW. So this is actually already, I think, maybe on the order of 6 months old, but I only just got a chance to play with it this week, and I'm really into it. So I decided to kind of, even though this was kind of probably more relevant to what we were doing in week 6 and 7 with generative models, I wanted to bring it in so that you guys could see it, because it's really cool, and it actually knocks off a few capabilities that we don't actually have with what we've learned so far. So GLOW is a generative model that was released by OpenAI, and what it does is it allows you to project images back into the latent space. So what do I mean by that? And we'll kind of go through these in a second. One of the big problems that you have in generative models is reversibility. So recall that in all generative models, most generative models, you usually have some sort of a generator, which is typically a neural network, which takes in some ostensibly random input vector of just random noise. Fairy dust, we call it sometimes, or I do anyway. And then it outputs real images. Now it goes forward only one way, right? Random noise to output image. However, this leaves open the question, can you do the opposite? Can you re-encode an output image back into the latent space so that you have its representation within the neural network that's capable of reproducing it? Because if you do, that would open up some really nice possibilities. And in autoencoders, technically there is an encoder, right? You can take an image and use the encoder to project it into the latent space. However, it's only approximate, right? Because of course the reconstruction is not perfect. If you were to take one of these reconstructed samples on the bottom and then plug it back into the encoder, it wouldn't give you the exact same latent variable. So autoencoders have a way of doing this in principle, but it's approximate. GANs don't have a way of doing this at all because there's no, or at least vanilla GANs, right? Because there's nothing connecting to the generator. It's basically just a loose latent variable and there's no encoder, right? So now there are hybrid models like VAE GANs that do have an encoder, like on top of that generator, but then you just have the same problem that you have with autoencoders. It's approximate, right? Now it would be very desirable to be able to have a perfect reversibility, so that X, the image, you can get Z from it. You can get the latent variable that produces the pixels X, and you can go back the other way, right? Or rather, you can, of course, as always, you can project the latent variable Z into the image X, and then you can also go the other way. And it turns out that this is possible, and there's a little paper trail that you're encouraged to read if you're interested, what are called flow-based models, and these kind of originate maybe in 2014. And the idea is that these have perfect reversibility. So they're invertible functions, right? There's a notion of invertible function. You have some data space X that may look like this. You can project it into your latent space Z. My mouse is back magically. I don't know. Keynote is very mysterious. Anyway, and then you can then also do the reverse. You can go back from this identical latent space Z and recover your data space X. And the math behind this is not for the faint of heart. We're not going to cover it because it's pretty out there. But definitely, like, you're encouraged to read it. And the way that the GLOW people do it at OpenAI. Yes, exactly. The way that the GLOW people do it is is actually using these special 1-by-1 convolutions, invertible convolutions with 1-by-1 filters. So it turns out that and they apply something of like analogous to rotation of the data, like a matrix. So those are really cool, and they allow us to do reversibility. So now, why is that interesting? What is good about that? Well, once you have reversibility, that means suppose you have a generative model that's able to synthesize faces, right? We have this generative model that's able to synthesize faces, And then I can take a face that wasn't in the original data set and find the latent variable z, which if you input it into the generator, it would produce that exact image, right? So this is actually a photograph of me, right? Or it looks like a photograph of me, it's identical to an actual photograph of me. But what it is actually the result of a generative model synthesizing it. So the model is capable of synthesizing this exact photo because I'm able to project that photo into the latent space and get that variable z, the latent variable z that produced it, and then we have it. Now, why is that cool? Well, recall that when you have a latent variable z, there's all sorts of things that you can do to it, right? Like I think, well, okay, I don't have any figures in it in the slides here, but you can make transformations to z and then try to produce a new image, right? So, and you remember in DCGAN, there's all these feature vectors that are floating around. You can put glasses on people. You can, you can do things like arithmetic, man minus woman plus woman with glasses, or what is it, equals man with glasses, right? Things like that. You're able to do arithmetic on the latent space. So, in this case, with the GLOW models, which are pre-trained, they have pre-trained models that are released here, you're able to do things like, okay, project your face into it and then turn your hair blonde, put glasses on yourself, put a lot of makeup on, make your hairline receding, make yourself aged, all sorts of things. It's really, really kind of neat, and that's how these were made. And you can also do interpolations between two different faces, right? So here I've encoded myself and Justin Bieber. Why Justin Bieber? I'm a big fan. And so what happens here is I projected both faces into the latent space. So you have these two variables, z1, z2, and then you could draw a line between them. A line, or you can traverse it in various ways, like spherical interpolation is actually better, but in any case, like if you draw a line between them, and then at each point in the line you interpolate along it, and then take that latent variable and decode it into image space, and you get sort of plausible face in between. And all of the faces are roughly plausible because it's a generative model of faces, and so you can see the resemblance, right? I've been kind of thinking about changing careers. So. This is, and it's very generalizable. Okay, so there's me being turned into all of the politicians of the world. Obviously, like Kim Jong-un is the best. The Putin one is actually very smooth, if you notice. Like the hair slowly recedes, and then, yeah. So that's Angela Merkel, Obama, Trump, May, Putin, and okay, well, so I'm going to show you this notebook that'll show you how to do these things, basically. And it just shows a few relatively simple things. And I think, so let's just think about this. Yeah, I think that'll be what we do. I just wanted to actually bring up a joke. So the first time I messed with these was actually with the app FaceApp around 6 months ago, or maybe a year ago now. I think that app was around. Did you guys remember FaceApp? It was this app that you can download on the iPhone App Store and maybe Android, that would let you take a picture and put a smile on it, right? So this is a fake smile. I don't really smile like that. And I thought it would be really funny to mess with it a little bit. So I did this little trick where I would just take the output. This is a very manual process because it's not like there's an API. I would take this and then I would make it smile again, and then take the output of that and make it smile again. I did this over and over and over until it couldn't detect the face anymore. Yeah, and then it stops right over here on the Aphex Twin frame. So anyway, you can do this kind of stuff now actually programmatically instead of manually like I was doing. That was maybe a year ago now, I guess. Okay, so I'm going to show you how to do this demo. You can find it on, I'll probably merge this into MLFray at some point, but right now it's just under my GitHub. And it's just a fork of OpenAI's GLOW. And the OpenAI GLOW notebook is actually quite fine, but this just has a few convenience things that'll make it a little easier. And I'm actually going to just get out of the slides, and I'm going to set up. Oops. Okay, Okay, so I'm going to actually, I hope this works. Yes, okay, good. This is, oh no, not there. Yes, okay. CDH, okay. This is actually just my home, so I have a home server. I'm not using Paperspace for this because I just haven't set it up yet, but you could in principle do this in Paperspace. And now I'm just going to connect to it. I've done this exact procedure where I set up a tunnel between the Jupyter Notebook, remote Jupyter Notebook, and my local computer so many times that it's like basically muscle memory by now. Oh yeah. So you guys, hopefully, if you've been doing a lot of this, you should be pretty used to it by now as well. Okay, so that's running. I can copy this and just change it to 8157. Okay, so now what I'll do is I'm inside Glow. This is just what Glow looks like, and just so you guys have a sense of it. Yeah, this is the blog post about it. It's really a nice blog post, very, very accessible. I'd recommend you guys read that if you're interested in knowing a little bit more. And then, yeah, so this describes it and has just a little online demo. I already showed you these screenshots. And then here's the GitHub here's their code repository, and then my fork of it has this notebook inside, which is, where is it? It is inside, oh, it's inside of demo. And then you'll see this demo notebook. So the idea is that first you just have to do a little bit of setting up. There's this script that you run. I've already done this, so I'm going to skip that. One thing to note, and I've written this down in a notebook, I had problems using, there's kind of two models you can download. There's a so-called optimized one, and there's an unoptimized one. The optimized one for me doesn't work. I think it's because this block parse thing that you have to install for some reason just didn't install in my system. But the unoptimized one seems to work just fine. So if you get the same thing, you just have to change this optimized equals false flag inside of model.py, and you'll see that at the top. So basically, this will just, the first thing it'll do is it'll just load all of the methods from model.py. That's kind of the main, yeah, like the main thing, the main code base. So that'll take, it usually just takes a minute because it has to kind of do a single quick forward pass. So it says loaded model, but it's actually going to say warming up the model or something like that. And then what we'll do is, so the thing is that it has a requirement that faces that you put into it are perfectly aligned. So the eyes are kind of in the middle, and the face kind of fits a standard rectangle. Okay, so it's done now. And I'm just going to use myself here. So that's the test image. There's this, they have a utility script called align face, which will take an image, right? Like it'll take basically, let's say this image. And this one is, okay, this one is actually pretty aligned already, but the point is, like, let's say it wasn't exactly aligned. It'll give you a 256 by 256 square where the eyes are exactly in the center. So I'm going to run this. Okay, so there I am. And if it gives you nothing, it means it didn't find the face, and it might be because the face is too small within the frame of the image. Just kind of crop it around the shoulders. Yeah, you can see it kind of got rid of my shoulders. And then basically, okay, so now this is it's fairly simple. You just kind of, you have to reshape it into a tensor of size 1 by 256 by 256 by 3. The 1 is because it's like a batch size of 1. So, and then you run encode to get Z. So because these are, so I'll run this, and then it'll give me, here's the shape of Z. Why is it this big? So that's just, it's just 256 by 256 by 3, 196,000. So the latent space variable is actually the same size as the input. And that's because the convolutions are 1 by 1. They're perfectly invertible. So you get the exact same amount of activations at each layer. This is why it's called a flow-based model. So like the activation is always like consistently 256 by 256 at each volume, and then they're just kind of like gradually changing. So those details are not super important for us, but it's kind of interesting. The fact that that Z is so large instead of what we're usually dealing with, which is like 100 or 1,000, is makes it kind of unwieldy. So it's like a little bit difficult to do, sort of random permutations, because none of the individual elements are very, very meaningful. They're only meaningful together. So you can't just like modulate one and expect very much change. So I'm still kind of playing with this to figure out ways of like messing with Z a little bit, but this notebook has the ways that are at least straightforward enough to do now. So okay, so here's the idea. So I have Z, right? So then I'm actually going to, there's a function called decode, which will convert any latent variable Z into an image X. So if we do x new equals decode Z, and then we show x new, you have to grab the first one, because again it gives you back a tensor, so you just grab the first, like the first image within it. There's only one, but it's the first of one. So if you run this, you'll see that it's the exact same image, right? This is not x, it's x new, but it's probably with I think it is exact. I think it should be exact. Anyway, it's certainly, you can't tell any differences. Okay, so like what can we do? So one thing we can do is, oh, of course I already like made some changes to this. These are the available tags that you have. What are these tags? So the idea with GLOW, and you can read about this actually here, is that within the demo, there is they're using this celeb AHQ data set, which is a whole bunch of faces of celebrities, and the celebrity, those images are tagged with I think 40 attributes, just binary tags, like, okay, so 5 o'clock shadow, or no 5 o'clock shadow, right? Arched eyebrows, attractive, very subjective obviously, bags under eyes, bald, bangs, big lips, big nose, black hair, blonde hair, blurry, brown hair, and so on, bushy, let's see, bushy eyebrows, chubby, double chin, eyeglasses, goatee, gray hair, heavy makeup, high cheekbones, male, mouth slightly open, mustache, narrow eyes, no beard, oval face, pale skin, pointy nose, receding hairline, rosy cheeks, sideburns, smiling, straight hair, wavy hair, wearing earrings, wearing hat, wearing lipstick, wearing necklace, wearing necktie, and young. Some of these, you'll notice that there's young but not old, and there's male but not female. The point is that for opposites, the attribute vector for the opposite is just a negative of you'll see this in a second. So we can kind of go in both directions. So okay, so first of all, we split these tags into an array of strings, and this is how this works. I'm going to copy Z, and then I'm just going to modify it, and we'll call it Z blonde. And Z blonde is going to use, there's this function Z manipulate, which will take this blonde, like blonde hair tag, and it will grab the manipulation vector. So what is this manipulation vector? It's like a delta Z. It's basically another 19,000 or whatever it was element vector, which tells you the direction in which things become more and more blonde-haired, right? And so what you can do is, I can do a plus equals. That means we'll add to it. We'll add to Z blonde. Z blonde right now is just Z, right? But I'm calling it Z blonde, and we're going to add to it 0.99 times this. So if we added just okay, well let's actually try this, right? And then it'll decode it and it'll draw it, right? So I'm going to run this, and then it's going to do. It'll do blonde hair, goatee, and young. Okay, so there's my blonde hair. There's me with the goatee, and oh, this is okay. So now, oh yeah, that's right. I'm going in the opposite direction. So I'm doing plus equals 1.2 times young. It's a weird thing. So like young is flipped. It's actually there's a little thing in the model script that I don't know why, for some reason it comes flipped, but then they deflip it. You'll figure it out. So it's like little things like that. So for example, okay, if I did minus, so if I did minus young, then I'd be adding. So instead of being older, I should be getting younger. Yeah, exactly. Yeah, that's me younger. right? And then also, let's try to subtract male. Let's see what that comes out like. I haven't tried this. So that's me increasingly female. Does anyone want to try this? Anyone want to get pictures taken of them and have themselves projected?
Does this only work with portraits?
Yeah, kind of. It doesn't. I mean, you can like if you mean is your face kind of leaning to the side or something like that?
Or like you wanted to use something a different subject matter.
Oh no. I mean, in theory that could be trained for that, but this model that we have is a face model. So it would. I mean, in principle, it'll take any pixels and projects it in. But then if you try to do some sort of an operation on it and it's not actually a face, it'll probably come out mushy. So that sounds like you just volunteered. So no, I'm just kidding. No one has to be in the video. All right, this is why I use myself as subject matter. But if anyone does want to volunteer, then, does anyone want to see themselves converted into Kanye? Yeah? Who's going to be the guinea pig? Nobody? All right, then I'll do it. Going once.
I can do it.
Yeah?
Yeah.
All right. I need a picture of you.
Did I take
Oh, yeah. Frontal. Make sure it's like good lighting. Yeah.
With glasses, without glasses?
Actually, without glasses, yeah. It does get a little. Okay, we have Itai. And I'm going to throw this in here. Okay, first image is going to be Itai and Kanye. All right, so now we're going to get Itai and Kanye. Oops, what's going on here?
The alignment photo.
Sorry?
Do you have the video alignment on this?
No, but it should be fine. Oh, okay. It's one of these things where the camera like makes it.
Did you restart recording?
Sorry?
Did you restart recording?
Yeah. Yeah. Okay, so now this should work. Okay, cool. There we go. So now, like, let's do. Yeah, so we'll do in the range of 8. All right. Okay. Okay. Actually, let's do an experiment. So what I'll do is let's say like in 80 frames, and we won't actually just show them. We're just gonna save them. So you could do to save frames. You could do like import scipy.mist and then scipy.mist. What is it? IM-save, I think. And then we could do like frame 05d.png. And that's going to be and that's going to be image tween. And actually, let's do I+1. And let's put that into a temporary folder so it doesn't get inside of here. So temp. And then we can ffmpeg -i. And we'll make a GIF. itaikanye.gif. I think that should work. So 80 of these. Oh, and then this has to be like this. Okay, so now I'm going to run this. And okay, already a problem. What did I do? Array does not image tweet. Okay, so that's working. And here's temp. Here's our frames. Great. Okay, so now we're going to. This will be wonderful. I promise. Absolutely. Okay, it's going to go to 80, then it'll stop. Oh, what happened there. Let's just go. Okay, so it's cd demo ffmpeg -i temp and then frame Itai Kanye. All right, let's oh, well.
Maybe better off opening it up in Chrome.
Yeah, right. Yeah. Here, I'll just. Oh, I forgot to do it the other way around. That's good, huh? You see, have you ever seen them in the same room together? I'm just saying. Okay, so we're just gonna watch this for the rest of the class. Anybody else? Does anyone have any other suggestions? Any other images we could use? Turn it into the Queen of England, yeah.
What's happening with the background in these? Is it effectively just like noise from?
Kind of. It's like sort of plausible backgroundish, you know, because it doesn't really focus on backgrounds, and the backgrounds are all different, so it doesn't really learn very many background-esque features, but it has to, you know, it finds some sort of a like reasonable interpolation. Actually, I find that most of them seem to kind of go blank in the middle. Yeah.
The beard is pretty accurate, like between
the beard, yeah. Sometimes I find it does weird things. Like, okay, when you interpolate between in between these two sort of vectors, you might go through a region of the latent space that temporarily puts a beard on it, and then like let's say you're going from one person not with a beard and then one person with not a beard. There'll be an intermediate stage where it has a beard for some reason. So anyway, so that's cool, right? And you can also, a few other things that we can show how to do. Oh, what's going on here? I thought I must have fixed that. Let me quickly recover this. Git fetch. Okay, cool. Let's actually get out of this and go back into it, because I had made some changes to it, and yeah, there we go. So another thing you can do is, let me just go ahead and run this, is that you can basically just make random faces, and that's the, you know, like, okay, so Z vector is just, you can just generate Z's, right? And the thing is that Z is sampled. All of the Z vectors are sampled from a standard normal distribution, like just a Gaussian, multivariable Gaussian, and really multivariable. So 19,000 dimensions or whatever, or is it 190,000? I forget. 19,000. And now what happens is that you sample the vector and then you multiply it by a scalar called temperature. And the temperature kind of like, if you have a very small vector, like the magnitude of it is very small, like let's say 0 basically, then you'll get like the same face all the time. The higher the temperature goes, the more the face will become, yeah, let's try this. The more that the face is going to be kind of like noisy, but there's more diversity. So like, okay, I'll run this again. Oh, yeah. So it's the same thing all the time, you know, so like this really obviously reveals the character of this data set. But basically, yeah, same thing all the time, and then increasingly more and more. Like when the temperature goes really high, it just becomes really crazy, yeah. You can kind of see what's going on there. Let's try really like, let's do like 1.95. I'm actually curious how that comes out. Oh god, yeah, okay. So we've managed to just explode the face altogether. Maybe like at 115 it might still be. Basically nothing above 1. It's gonna work. Yeah. So that's Glow. Really neat stuff. You can project real images back into it. You can do operations on latent space. You can add multiple vectors, right? You can make yourself blonde-haired and with glasses. You can make yourself aged. Yeah, you can do all sorts of things.
Would it like fail if I don't feed face? Like if I just put random stuff, will it like run anyways? Will it try to do something? Or?
It will try to do something. It'll just become mushy. It's worth trying. Like I did a little bit of that, and it's. But you have to then skip this align face thing because it won't find that face.
Right.
Oh, let's actually, since we have Itai in here, let's go ahead and make him look old and stuff. You signed up for more than you bargained for, right? So okay, now we're gonna project you. Here's your vector. Doesn't it feel very personal? You know, like this is you. Yeah. And then we'll decode it. Okay, and then we're gonna make you blonde, goatee, and more female. Blonde, goatee, more female. Let's make you young or old. So let's do, yeah, let's say like 0.75. Okay, that's really young. And then really old, let's add it. So you see it's the opposite of what it should be. So you can just, if you multiply it by -1, then it'll make more sense. You look exactly the same. It's telling you something, you know, what's going on. Maybe it doesn't, it does better in youngifying than oldifying, but okay, let's try it, 0.99. There we go, that's a little more aged. Are there any others that we want to try? Attractive? Heavy makeup is pretty good. What's that? Bald. I find that the bald one doesn't quite work. Receding hairline is better. So let's do bald, and then we'll do receding hairline, because I think that one somehow works better. And then let's also do double chin. Eyeglasses. We'll put glasses on you. The double chin one doesn't do anything, I've noticed. I don't know. Some of them are kind of weird.
So just to be clear, these tags are
from the Celeb HQ data set.
Okay, and that's what this particular model is based on?
Yeah.
But you could train your own.
You could, but like look up the documentation for training. It's like outrageous. Like I think yeah, these OpenAI threw like tons of GPUs on it. It's like prohibitively. I mean, and it doesn't really say how much they need. They have scripts for training it, and you know they all use like 8 GPUs, and like they take a long time. I think. I'm not about to try to train them. And also, of course, like you have to get a data set and stuff. It's definitely worth doing. Like, but it may be something we have to all look at together to see how plausible it is. Anyway, oh look at that. There's your glasses. I think the glass sector needs to go a little higher. What about? Okay, well now we're just getting a little bit out of control, aren't we? Oh, let's make you female. Female. So subtract 100% of your maleness.
The top one, the bottom one?
Yeah, that's it. Doesn't Yeah, you can see. Oh yeah, and that's not so bad. Okay, it erases some of your hair. So anyway, that's Glow. Any questions? Yeah, fun stuff. So many possibilities, right? Okay, let's go back to the slides. The other thing that I wanted to show you was the BIGGAN demo. So again, this was just released yesterday. So I showed you BIGGAN's like already. I've been showing it to you occasionally every week. And as it so happens, the models that were producing all of these hyper-realistic images have been released. There's 1,000 different classes inside of one model. So it's really, really like, and it's really large. It's a very large model. Also, like, extremely difficult to train. I'm not about to train these, but there is documentation for training it. But I would definitely like know what you're doing first before looking into it. And I just put up this notebook, and I'll share the link with you guys later. But this notebook, assuming that I did it correctly, should be public right now. It's actually just a fork of the notebook that. Oh, actually, let me do it from here. It's just a fork of the notebook that the OpenAI put out. Sorry, Glow was made by. Oh, it was also OpenAI, right? Sorry, I'm confusing things. BIGGANs are made by NVIDIA. So they released a collab demo, which is really nice because it's just free Google GPU to run these, and so you can just run this from your browser. It's pretty nice. The original demo that they released was a little unwieldy because it would generate the images and display them in a notebook, but then getting stuff out of there is a little tricky. So the main thing that I added to this is basically the ability to link it to your Google Drive, which is actually pretty easy, and then save the frames to Google Drive, and then you can download them from there. And so you can make videos from there. There are 3 models that they have. They have a 128, 256, and 512 one. I'm not even going to bother with the tiny ones. Like, why not go straight for the big one? It's not as big as the progressive GANs, which are 1024, but it is much more realistic. So then you would run this setup. It takes a little. Okay, so it imports all this stuff, and then basically it'll load the actual module. And I hope I don't have too many things running right now. Let me check. Oh, oops. Okay, yeah, that's fine. So then I'll run this. Okay, so it's gonna load it. It'll take just a moment. And you can see that it's thinking right now, initializing. And then, yeah, there we are. Okay. Now I'm going to, these are all just a bunch of functions that we're going to use, and we don't have to look at them, but like they're just TensorFlow stuff. So basically setting up your Z and Y grid and so on, more or less. And we're going to use these kind of as an API. They have like some nice convenience functions. If you want to display it within a notebook, you can use IMShow. So we'll define that, then we'll start a TensorFlow session. And then, okay, so they have these like interactive GUIs. I'm actually going to skip this section. Okay, so we can look at it really quickly. But basically, this lets you just like, okay, pick. Let's say there's 1,000 categories, so it's really, really a lot. Hang on a second. So like, it's really nice these like built-in GUIs. So I don't know. You find something you guys like? Sundial. Suit?
Schooner.
What is a schooner? A what, sorry?
Sailboat.
A what?
Sailboat.
Oh, sailboat, okay. Okay, so it'll generate 10 samples. And actually, I'm not sure what this truncation variable is. I'll have to read that. I'm not 100% sure what that is. Okay. So, and then I'll just display it in here. And if you double click on the gray rectangle, it'll actually just bring up the code. It's awesome, right? You can see the code that if you just double click in here, this is how you set up these GUIs, and then it goes, okay, like this truncated Z sample. So it'll basically like generate this many samples, so 10 samples. It'll give you like a matrix of like a tensor of Z values, where the number of rows is the number of samples that you're generating. And then it does all the batching and everything automatically, so we don't have to deal with that. The next cell is much more interesting. Oh, yeah. you can interpolate between BIGGAN samples, and here this is where I actually modified it a little bit. So what it'll do instead is it goes, okay, well, how many videos do you want to make? Let's just say 50 interpolation frames in between, and then it'll actually and then say, okay, how many interpolations in one video? So 6. That means it'll go from 6 classes and times 50 frames for each one. So basically this will, I should make this a little, it makes more sense if the variables would be here, but okay. So I'll define this, and then this is the get random interpolation. Oh, it actually just overrides and says 8. I should really, okay, that's fine. I need to modify this just a little bit. It's a little hacky because I made it at like 3 a.m. last night. The things. Okay. So I've written that, and then basically you can, I found that you can actually save files locally within the notebook, but then once you start downloading a lot of them, it actually becomes super annoying. And so what I did instead is you can use this code to link the notebook to your Google Drive. So if you run this right here, it'll actually bring up like a little authentication. Oh, I have already mounted it. Well, what'll happen is if you run it for the first time, it'll bring up it says click here, and then you go and it gives you an access token, and then you throw it into a little inside the cell, it'll give you a little a password box. You put in the token, and then the drive is mounted. So your Google Drive is linked to this notebook, and then here this will go. Okay, let's just make 3 of them. So I'll actually, yeah, let me quickly do this also. So new folder, ITP frames. Okay, so let's go to ITP frames. So it's empty right now, you see. And now what I'll do is, from the notebook, I'll go, let's generate 3 videos, and I'll say put these into ITP frames. So this will go content, G drive, my drive, ITP frames, and then it'll save the frames individually. So let's just do 1. I think is fine. And I will go ahead and run the cell. I think I'm doing it right. Yeah. So what it does is actually just pick 8 classes at random: screen, ladle, bee, bagel, capuchin, flamingo, clog, pattern, sap. I don't know what a lot of these things are. Again, this is ImageNet, so 100 classes are dogs, something like that. So is that a beagle or a bagel? Oh, bagel. Okay. So I was generating the images, and yeah, this will take a moment, but you can see, okay, it's really easy. So I'm going to share the link with you, and what you have to do is as with Colab notebooks, you have to mount it to your drive. You have to download the Colab. Enable Colab, download it, mount it on your drive, and then you just run through these cells, and so you can be making these in no time.
So could we replace everything we're doing using Paperspace 4 with Colab and G-Drive?
Possibly. There's some aspects of it that may be a little annoying to use. So first of all, it's slower because they throttle it. So if you're trying to train pix to pix, it takes a long time, I think. Or maybe I don't know. I might be wrong about that, but it's worth looking into. I haven't done it fully yet. They also don't necessarily make it easy to do really long jobs. It'll time out if you're idle. It kind of disconnects randomly. It's still a little bit of a work in progress. In principle, in theory, you can, although there are some permissions that are restricted. So it's definitely worth, and also it doesn't it's not necessarily easy to set up PyTorch or whatever, right? So it works flawlessly with TensorFlow, but definitely it's worth trying, but you may run into problems. So okay, you see that it's downloading these frames. So right now it's actually saving them to my drive. We can look and see that they're already here, right? And let's just actually stop it, and what I'll do is oh, it's already stopped, right? So basically now I'm going to go back to here, and I'm just going to download ITP frames. Okay. So it also can take a little while to... Okay, well, I'll let this go for now, and then we'll get back to it, and we'll see what we generated on the fly. Okay, so here's what we'll do actually, and what we'll do now, I'll just show you, like, as long as if this downloaded quickly, I'm gonna save the music stuff for after the break. So we'll actually, let's go ahead and stop to take a break now, and then when we come back, like, this should be ready, and then we can move into music information retrieval stuff. Cool. All right. So for this second half of today, I wanted to introduce music information retrieval and start talking about some interesting things that we can do with audio, and also get into things like WaveNet, which of course is something we've glossed over a little bit, but is of course very relevant to a lot of this generative model stuff. And there's a lot that music information retrieval can kind of it may at first seem like a lot of things that are not necessarily perfectly relevant to the class, but there's actually a lot of things within it that become useful in a sort of sideways way. Oh, sorry. Okay. So what is music information retrieval? How many people have some familiarity with this field? Okay, a handful of you. Obviously, like if you're using things like MaxMSP, you might already be familiar with it. Music information retrieval actually has some personal value for me, so it's actually kind of the way that I became interested in machine learning to begin with. So when I was in college, I was like really curious about music recommendation systems. I was like, I want to find new music. What's a cool way to do this? And at the time, this was still in the early. This is sort of pre-social media, so there wasn't really a lot of social media, but there was Last.fm. And how many people know Last.fm? Of course, like still around today. It's kind of a shell of its former self. But when back when I was using Last.fm, it was just an independent company. They got bought by CBS or someone really random. Yeah. Anyhow, before then, Last.fm had this software that they developed called AudioScrobbler, which would let you basically keep track of all of the music you were listening to. It was a little plugin that you could install in like Winamp and whatever other like media players you were using, and it would just keep track of all of the songs that you listened to, and you'd build up a big long history. And this was sort of before things like quantified self were in the lexicon. I was just interested in logging all of my listening history, and I'm still doing it actually. But the idea was, can you? At the time, the idea of music recommendation was entirely social based, using a technique called collaborative filtering. So the idea behind collaborative filtering is if you want to do recommendation of music and you have everyone's listening data, then people with similar listening profiles are the ones that are going to have recommendations for you, right? So you look for music that people with similar tastes to you listen to that you haven't listened to yet. And so that was kind of the basis for music information retrieval, and for music recommendation, and for the most part still is, because it's harder to do it through the audio itself. Although we'll talk about that in just a bit. Other things that music information retrieval can do. So I would kind of broadly categorize some of the classical tasks in MIR into sort of these four categories. So you have identification, so like finding audio. So fingerprinting means identifying a recording as being a particular canonical recording. So, and this is what Shazam does, right? And SoundHound and all those kinds of apps that you are in a crowded bar listening to music, and you you record a little bit of it, and it's identified very quickly, which is really, really quite impressive if you think about it. I remember being very impressed by Shazam the first time around, and learning a little bit about how it works. And it's actually like, to defeat this sort of crowded bar problem is not trivial, but they do it in a particularly elegant way, which maybe if we have enough time today, we might actually look into that, because it's actually just kind of interesting. Related to fingerprinting is cover song detection, and that's kind of a more specific instance of IDing a particular song, whether or not. So the difference between fingerprinting And cover song detection is the difference between a song and a recording. So fingerprinting is finding a particular recording, and cover song detection is finding a rendition of a particular song, whether or not it was, it could be played live, it could be played by another artist, and so on. Another cool area is like, can you query music by humming it or whistling it? So that's another pretty neat application that people are interested in. Detecting artists and detecting instruments, to fill out some of the things that you know about the audio is also very much relevant. Now, the analysis of the actual audio itself, so beat tracking, detecting the key or the mode, transcribing it, so pulling out the melody, pulling out the counterpoint, pulling out the chords, and so on. The segmentation of audio into its respective parts, verses and choruses, and so on. This one is a really big one, is source separation, so unmixing, basically. So can you take a song with 4 instruments and then turn it into 4 recordings of each of those instruments isolated? That's a really hard problem because of the additive nature of audio. And so it's really difficult to unmix, but it turns out that is something that you can do. Incidentally, WaveNet is a particular way of doing it now. Metadata inference, so I'm trying to pad the information that you have about a piece of music. So what genre it belongs to, maybe some of the tag words that are relevant to it. Last.fm, of course, has a lot of tagging functionality. That's how they learn about music. As do lots of other social media sites. So obviously this is very relevant to be able to describe music in natural language. And recommendation applications. So creating playlists that have various properties, recommending new music. And this is a cool one, is hit song prediction. So that's $1 billion task. So can you predict if a song is going to be a hit or not? So that's a pretty neat one, right? So recommendation is fair enough because it's for one person, right? One person is, well, it's hard to say who's more predictable, one person or many. It's actually hard to say. Maybe one is more predictable in some ways and the other is more predictable in the others. But anyway, this is a really nice resource, by the way. I actually just found it the other day. musicinformationretrieval.com, and it has a lot of Jupyter notebooks for doing some of these tasks. So I would definitely check that out. It's important to understand that, like, what we mean by audio, right? Because there's multiple ways of actually turning audio or music into data. So we've had symbolic approaches to representing music for centuries, right? Of course, music notation is now centuries old. MIDI is not a century old, but half a century old or so. There's other various representations that you can think of. Tabs, for example, is another way. ABC notation is also very popular. And then there's the raw audio itself, right? Recordings. And then, of course, a song can be on the metadata level as well. So, talking about things like the information about the song. So the artist, the year, genre, what album it's from, tags, who's listening to it, and so on. So these are all sort of ways of representing music and kind of getting data from it. Now, the MIR pipeline, when I was getting into it, looked like this. Where's my mouse? Yeah, again, there's no mouse. It disappears and comes and goes when it pleases. Yeah. Anyway. Maybe if I get out and then go back in. No, that didn't work. Okay. So the classical pipeline was, and we kind of, let's first look at this. Remember, I showed this in the first week, I believe. The idea that deep learning has kind of changed computer vision by taking what used to be a hand-engineered process, extracting features and a representation of the image, which is not just raw pixels, and then turning it into some more compact, more high-level representation, and then plugging that into some shallow, so-called, learning algorithm like an SVM or a random forest or whatever, or a neural network. And what deep learning did was that it took all of the process of feature engineering and it made it part of the process of learning. So the features are actually learned in the process of training it to do whatever task it is supposed to do. And this has actually happened to MIR as well. So MIR used to be kind of like, basically, the field of MIR really was for DSP professionals, so people who are doing digital signal processing. And actually, okay, I did MIR stuff as an assistant researcher for here at NYU, actually, at Steinhardt, for professors there. And the job was almost 90% audio. It was like extracting features, figuring out representations of audio that would be useful for, SVMs mostly. That was the thing to do. And some of the features that were useful that we know of are things like MFCCs, frequency cepstral coefficients. For those who are familiar with those are basically, it's like it's a decomposition of audio into perceptually meaningful frequency bands. So it's not just like a raw FFT, but it's actually it's actually corresponds to these bands, frequency bands that have some basis in perception, tested from human subjects. There's also just like other kinds of spectral features, spectrograms obviously, and chromograms. Chromograms are the same as spectrograms except binned by notes, music notes, A, B, C, D, so on. There's also musicological features, obviously. So like key, or like chord progressions, or beats, time signature, tempo, and so on. And so you would get this representation from audio, and then try to apply a learning algorithm to learn things about it. So like what kind of things would we learn? So for me, I was working on the problem of mood classification. So some songs, they might be more energetic than others, or more happy, or more exciting, or sad, or whatever. And you want to be able to figure this out, and ideally figure it out from the audio, right? Because it's not obvious that you can get it from the title of the song, but you can get it from the audio potentially. How many of you listen to Pandora? Pandora radio station. That was probably one of the first internet radio stations that kind of tried to apply some of this kind of technology, but they did not do any DSP. They actually, because Pandora was supposed to do music recommendation, right? But the thing is that the way they had it was they had this, what they called the Music Genome Project, where they had interns, pretty much like an army of interns. Every new album, they would have to apply labels. They basically hand classify those songs according to like 200 characteristics that they came up with. So, how sad it is, or, does it have beats, or is it hip hop, or whatever. And obviously it was very slow at doing that, so it only scaled by a couple of albums per week because they had to hire people to do it. And so this is kind of a weakness. Ideally, it should work on the audio level, because then it can be done automatically, which means that it's not just open to, that means like obviously that would change the whole pipeline of music. You don't necessarily have to have gatekeepers like at Pandora. You could work on any new music that's submitted to it can actually be automatically extracted for features. And so Pandora didn't scale very well, yeah?
Did Pandora or anybody else use allmusic.com's database?
It's a very frequently purchased database of like various manually curated information.
Yeah.
I'm blanking. I think Rogi's the company that actually sells the database, and you'll find it in lots of different places, from Spotify to other services. But yeah, I don't know.
But like nobody's contributing to it anymore, right?
They hire writers specifically to contribute to it. I don't know what. I mean, like, it's a very expensive license. It's like thousands of dollars a month, or with annual contracts.
Obviously that it would be ideal to be able to just do it yourself, right, instead of relying on hand-labeled stuff, because of course it doesn't scale. Now what's happened in the last few years is that, and my own knowledge is a little bit out of date because I was much more active in this field about 10 years ago now, but MIR has been, of course, like everything else, has been penetrated by the deep learning tsunami, and obviously like there's a lot to gain from that, because as with computer vision, one thing about deep learning is that it seems to be more accurate, because you can only try so many features, but deep learning, like, it finds the features through gradient descent, and it optimizes the features that are particular for that task. So instead of, like trying to relearn a new set of features for every possible task that you want to do, you can actually just like keep reusing the same bits. It's of course like simplified a lot of the implementation. You don't have to deal with all of these different implementations of various feature extractors that need to be maintained themselves. It's very homogeneous, right? You just have this big neural network that learns all of it. So all of the advantages that you have with computer vision, you have with audio as well, as we do with text, as we'll see a little bit more next week or 2 weeks from now. And also it's worth noting that like one of the really cool things about this is that one basket of skills, the deep learning basket, lets you now work in computer vision and audio, because it's basically now suddenly like the same field. That didn't used to be the case, right? If you were specialized in computer vision and you knew all about these computer vision features that you could extract, and you knew a little bit about machine learning, that was your sort of base of skills. Now you know about machine learning, and it's just like the only thing you have to know about is that audio is a different set of bits than pixels. But otherwise, like the algorithms can be applied with superficial changes and still work. So. Isn't that cool? Some people are upset about that, but I like it. Yeah.
Have you seen this?
No. What is that?
The Sound of Pixels.
What is it?
It says a system that by watching large amounts of unlabeled videos learns to locate image regions which produce sounds and separate the input sounds into a set of them. So basically, I think they're just looking at images and guessing the music.
Yeah, right, and figuring out maybe like what part of the video is producing the sound. Yeah, that's cool. Now, that's similar to some of the things that I've seen, but I haven't seen that. I'll take a look at that in a bit. In any case, so like just a few things that we've already looked at, just to show you again. Of course, like we have this audio classifier, and we've already done a demo on this, so I don't really think there's much of a reason to use it again, but. Just to recall, like this is basically will let you train different kinds of sounds. Like, okay, if I want to train this to recognize like clicks and claps, so maybe like we'll do class 1 is going to be like, and then we'll put the threshold down here. So we'll say class label 2. Class label 3. Secret talent. I'll train that and then predict. Oh, it's not that great, is it? Maybe those are too similar, I think. No, it's not that bad. You just kind of got to train for longer. Obviously, I only gave it 55 samples, so it's not exactly amazing. But okay, so yeah.
Also, it's recording the silence in between as well.
Oh well, it kind of is a little. Maybe the threshold timer is probably too high. It probably recorded a lot of silence, yeah. But in principle, it's supposed to stop recording as soon as it gets below the red. I think it has a little delayed, so the old results will vary. But mainly training it longer helps. By a little bit longer. In any case, this sends OSC to over port 9000 message classification, so you can open this up in Max and processing, open frameworks, and then you can grab that message and then trigger events, right? So you can trigger sound-based events. So how is this working? Like, what does this have to do with MIR? So this is actually not doing any deep learning. I'm using actually I can't even remember now. It's what's the OFX audio analyzer, I think. It's an OpenFrameworks add-on that does a whole bunch of DSP. So getting spectral features within the frames, and then the feature vector that it forms is all those spectral features, because okay, it's across frames, so you get a lot of them, And so it just takes the average of each of the features and the standard deviation, and then that's your feature vector. And then it trains I also don't remember, either neural network or an SVM possibly, on top of those features. And the nice thing about DSP, and why I still use it for a lot of MIR stuff, is that the features are actually pretty good. So you can do a lot of stuff with classical MIR features, like this kind of stuff. There's no reason to really use deep learning for it. I mean, maybe it would do a little better, but it's probably, for the purposes of what the scope of this, it probably wouldn't do much better. Yeah, we'll need more sophisticated methods to do things like speech synthesis, but for things like distinguishing different kinds of sounds from each other, then this works pretty well. So that's AudioClassifier, and as you know, we also looked at Audio t-SNE Viewer, and I'm going to leave this aside because we actually did the whole demo a couple weeks ago, I believe, or I included it in the extra lecture notes for week 4, was it? In any case, some of you are already using this, which I'm very glad to see. So Audio t-SNE Viewer, also same thing. It'll just take a representation of the audio that comes from basic MIR type feature extraction, and then it just does some dimensionality reduction on it. Actually, I don't think it even does that. It just takes the raw feature vectors and then does t-SNE. And then you have this nice playback application in open frameworks. A lot of places you can take this. You can, I think maybe, who was working on trying to get this in 3D? I think, yeah. How did that go? Yeah?
It was okay. I used a lot of different sounds that didn't necessarily work as well as they could have, but yeah, it worked well.
Okay, cool. Yeah, so that's obviously available for you, yeah, like Audio t-SNE Viewer. Let's talk a little bit about some history. So there's a little bit of a soft part of the class. I'm really MIR was really I'm very interested in computer music stuff. So this will be kind of some stuff that's interesting. I want to talk a little bit about audio. So I think so audio recording, proper audio recording that you could play back, goes to the late 1870s or something like that. Those are some of the earliest recordings. That's what I thought it was. It actually turns out that there's recordings even from the 1860s, but they weren't, you couldn't play them back exactly. So there was an instrument called a photoaudiograph? Photoaudiograph or something. I can't remember exactly how to pronounce it. Is anyone familiar with this device? It looks kind of like a gramophone, but what it does is it actually just takes the vibrations in the air that sound produces, and then it draws them on glass or on film or something like that. And then only later, like 50 years later, they were able to turn those into actual listenable audio, because you could then use another technique to pull that out and turn it into a sound wave. And so there's some recordings you can listen to online of somebody singing in the 1860s. They're extremely grainy. They're very noisy and grainy, but they're the earliest recordings that we have. By the early 20th century, of course, gramophones were really good and microphones were really good. Pretty much almost as good as they are now. Pretty much that was one of the first things that we got right pretty well. And this is a recording. This is if you go to sound recording in Wikipedia, you'll find this picture of Blackfoot Mountain Chief being recorded by this ethnomusicologist. And it's we have recordings of people way back when. It's just I don't know how much to say about it, except that it's kind of interesting to think that these are some of the earliest some of the earliest records we have of people. So so fast forward about half a century, obviously a lot happened in that half century. You had big band music and jazz and all this kind of stuff, and recorded music. But we're interested in computer music, so I'm going to fast forward a little bit. Electronic music has its roots kind of in the 1940s, let's say, when it kind of first started working out proper. And in the 1940s, that was when people first started experimenting with tape decks. So tape decks, you could record audio onto magnetic tapes and then play it back, right? And this is still before cassette tapes, but you had these, large sort of reels that you could play. And so people started doing all sorts of cool things with tape decks. They started cutting them up and superimposing them on each other and playing them back at different speeds and so on. And this was the basis for what's called musique concrète, which is a French term for concrete music. So very French. And for those who are unfamiliar with this term, musique concrète was this sort of like one of the earliest sort of experimental electronic music genres, where all electronic music was experimental at that time, but basically what they were trying to do was using tape decks in interesting ways to create sounds that had never been heard before. Because if you think about it, like before musique concrète, the idea of like what electronic music did, or the production of music with electronic components, was it opened up the idea that you could synthesize sound. That sound wasn't something that had to be made in the physical world and recorded, that you could synthesize it, right? You could say that this is analogous to all that like class synthesis and deep dream stuff, right? So instead of visualizing neural networks by piping in real images, you can actually synthesize images which have properties. So you can do that with audio too, and that was kind of the basis for it in the 1940s. And so the first, like Pierre Schaeffer, who was like one of the, I guess, kind of invented the term, he was doing all this stuff like making sounds like that no one had ever heard before. Like no one could, and they sounded really weird. Like if you listen to any of Pierre Schaeffer's music, it's like these like strange spaceship sounding things, and it sounds kind of trite to us now. But at the time, it was like really, really radical. It was like making sounds that you couldn't make in the physical world, basically. By just extremely heavily modifying recorded sounds, because that was the only way to do it at the time. Fast forward a little bit more. So that's Pierre Schaeffer. This is Daphne Oram, who is also working with like tape decks. And this is Pauline Oliveros. If anyone is familiar with her, she's quite of course, well known because she was in New York for many, many years. This is I should have. Okay, who knows who the one on the bottom right is? Is he? I don't actually know if he's. I don't think he's English. It's Stockhausen, Karl-Heinz Stockhausen. Yeah, and these are all different time periods, but it turns out, I was doing some research on this yesterday, and it turns out also that around the same time, like 30s and 40s, there was parallel to this a sort of like burgeoning like electronic music movement in Japan also, and these are some of the composers that were kind of well known for participating in it. I think this guy Minao Shibata kind of brought musique concrète to Japan, and obviously like by the whatever it was 60s or 70s, you had Sony and Yamaha coming around, and other like Japanese manufacturers, and so they were kind of really instrumental also, and like because we focus a lot on like the stuff that was being developed usually in Europe and America, but there was actually like a great deal of stuff happening in Japan at the time. By the time it was like the 70s or 80s, everything was kind of like globalized. Okay, here's another toss-up question. Anybody recognize that building? Anybody know where that is? I'll give you a clue. It's in New York.
New York City?
New York City. Okay, it is Prentice Hall. It is located on 125th Street, so about 100 blocks up. What is it? That way. And it's a building that's owned by Columbia University. So I was an undergrad here. And Columbia is actually like a few blocks away from here. But at this little dumpy building, they had what's called the Columbia Princeton Music Center, a computer music center. And this is actually a really, really special place. And you wouldn't know it if you've ever been inside there, because it's actually like a really, really sort of like dumpy building. But there's a ton of history here. So a lot of the original experimentation with electronic and computer music was happening here. It was jointly owned by Columbia and Princeton. So the Columbia Princeton Computer Music Center, and it was I think built in the 1950s. And this device over here that looks kind of like a huge submarine panel is an RCA Mark II synthesizer. So this was, I believe it is considered to be the world's first like electronic music synthesizer. So like not a tape deck, but actually like a digital computer music synthesizer. And it's like the size of a submarine panel, right? It has all these weird dials and knobs and stuff. And it turns out it's still standing there today. So that's it over there in Prentice Hall. These are some of my favorite people, so they really got me into computer music. Does anyone know them? Anyone recognize them? So that's Brad Garton, who's a really, really big figure in computer music, and the head of the CMC. This is Douglas, on the right, that's Douglas Repetto, who started Dorkbot, if anyone's familiar with that. That was kind of really active here for a long time. It's no longer happening. And that's Terry Pender in the middle. Anyway, that device still makes sound. And like they get it out and play it every once in a while. The thing can basically fit into like a pocket watch now. Like you don't even need a smartphone. Like a smartphone is like way more than this could be done in basically like a Timex type device. And it makes, like it synthesizes audio. It synthesizes programmable music. And programmable music goes back to, let's say, the early 1960s. So we're going to listen to this. Okay, so listen to this. Yeah, so basically this is, what you're listening to was the first ever like programmable music recording. So that was actually like, basically, it wasn't a recording, it was actually synthesized from scratch, right? They made a program that made all of the samples of that recording. And it was done in 1961 in a gigantic computer, like the size of ITP, basically, made by IBM. And the lead engineer was this guy, Max Matthews, who is here in the bottom right. If anyone knows Max Matthews, very beloved figure in the computer music community, pioneer, figuring out how to do this stuff, and it was very active in computer music his whole life. So this is like, even in the 2000s, he was working with these like new kinds of musical instruments. So he died maybe about 5 years ago. Max Matthews is the namesake for Max MSP. So Max MSP, if you're ever wondering what Max is all about, it was named after him. So obviously like big contribution. He was the lead engineer in this project at IBM. Continuing forward. So going from like, let's say the 70s through the 80s, 90s, and even really into the 21st century, the dominant way of programmable music was what's called physical modeling. And physical modeling is modeling physics. So basically instruments, like let's say you want to create a synthetic guitar. Well, how would you do that? Well, what you would do is a physicist would figure out like what is the mechanics of a string, how a string actually vibrates. So it turns out that there's actually equations that describe it. Like the way that string vibration is modeled is using what's called Karplus-Strong algorithm, I think I might have mispronounced that, but that's basically what it is. And so you would model it as a program, and you would write an algorithm which would generate all the samples according to this physical algorithm, this physical model. And physical models can become increasingly complex and have many modules and so on. And these were really the kind of thing that like just got better and better and better through the 80s, 90s, and 2000s. Computers got faster, and so you could use a lot more complex signal chains. And a lot of this stuff was being carried out at Columbia, also I think at NYU as well, and at Princeton, where a lot of the early like physical models that would end up in like commercial software for electronic musicians was being developed here. So and if you go back to the 80s and 90s, you remember like what Moog synthesizers, let's say, sounded like. You know, it's sort of dinky. And that's because, you know, these models are kind of like, you know, we have to program them, and so a lot of the details kind of fall to the wayside. And this was for a long time the dominant model, and you might say still is. Like we're in the middle of a transition period now. You could say that this is still the dominant model for how commercial music like synthesis is done. However, that's beginning to shift now with the presence of deep learning stuff. And actually, before we get to that, I'll have one more slide about physical models. There's actually like a project that I worked on that I wanted to show you really quickly. So this is actually an electronic music flute, like a sort of flute. Did I show you this in the first day? I can't remember. I don't think so. Okay. So this is an instrument called a burl, and it's made by this fellow named Jeff Snyder, who is the head of the Princeton Laptop Orchestra, PLORC, and he makes music controllers. And what we did was, this is one of my first projects using machine learning in music, was basically creating software so that you could train a physical model to be controlled by one of these devices, right? So this is a controller that has a bunch of touch sensors and a breath pressure and embouchure sensor, and and so it's just a controller, so it gets all these values through the sensors, and then you have some physical model that might be implemented in Maximus P or something like that, and it's parametric. So there's a whole bunch of parameters, frequency, you know, carrier frequency, modulator frequency, whatever kinds of like parameters that you have. And then what do? You can use machine learning to train a neural network to convert the input parameters from the sensors to the output parameters that control the synthesizer. So we built software for doing this, and then we had this like world-class flautist come in and try to play it. So this is after he trained it, this guy Pedro Eustache. It's surprisingly expressive, right? And the cool thing is that you can train it to have any mapping that you want, right? You just give it examples. So this kind of inverts the way of doing, typically doing music, learning how to play musical instruments. You know, if you've ever learned how to play a musical instrument, you know that it takes you like a long time before you can be creative or expressive with it. You have to learn how to make sound with it. And this kind of inverts that. This says like the instrument learns you, so to speak. So you give it a lot of examples, and it learns like how to make sound based on how you're maneuvering it. Now, what's been happening over the last couple of years is that now deep learning is kind of making inroads in this, and for many years, again, like for everything that we were synthesizing sound with, we were using physical models. So when you even now, when you run the command say, like, hello ITP, how are you today?
Hello ITP, how are you today?
So that's a physical model that's implemented, that implements like a vocal model, right? Like a vocal cord model. And what's beginning to happen now is that we can actually do this instead of using physical models. We can do it using recordings and machine learning on top of those recordings. And now, what would be the advantage of that, right? Well, the advantage is once you can do it with machine learning, you can automate the process of learning a model for any given set of recordings. So obviously, that's, you know, if we wanted to make random sounds of objects that we become interested in, it's inconceivable to like have to sit down and figure out a physical model that'll produce all of them. So it would be a lot better if we could just like throw hours of recordings at it and have it figured out on its own. And that's actually what we're beginning to be able to do. And I have to tell you, like when I became interested in music information retrieval, like in audio, let's say in 2008, this was on the horizon. Like people talked about this idea, but they talked about it only in the following context, that it was impossible. And I really thought it was impossible because here's the thing about audio. 1 second of audio is 44,000 numbers, right? That's the sample rate of standard audio. And to predict for a sequence of 44,000 numbers using machine learning, like using, let's say, an RNN or something like that, should produce junk, right? It just seems that way. But it turns out that it's almost junk still, but with RNNs. But we're actually starting to make plausible sound. The first time that I tried this, I guess maybe 3 years ago, let's say, when this guy Matt Vitelli, who I think did this for one of the Stanford classes as a project, but he tried to throw GRU units at it. GRU is a type of RNN. It's like similar to an LSTM, but it's not actually an LSTM. But basically, it's a recurrent neural network that tries to learn to model audio. To model so you just throw hours of music recordings at it, and then it trains a model, and then it tries to synthesize music that sounds like the audio that you gave it, using recurrent neural networks. So, and I think I have, let me just see here. Yeah, I have these sounds. Okay, so like so he put out the software online, and I tried it on, I tried to train it on John Coltrane's Blue Train. Oh, sorry, that's Chopin. And I heard that, I was like, oh my god, I just synthesized Chopin, right? Like, because it sounds kind of like Chopin, right? You hear the piano notes. It turns out though that it was actually cheating. I didn't know. It was overfit. These things were really overfitting. So that was actually, like, it basically cut a piece of actual Chopin and just like tried to pass it off as a new recording by throwing a ton of noise on top of it. So it cheated. Same thing for this Blue Train. This is Blue Train by John Coltrane. It's basically just the recording. It's actually like Coltrane plus a whole ton of noise. So it was overfitting, but it turns out that you could still do some cool things with it. So I found this sample of a vibraphone. This is an actual vibraphone sample. It's very repetitive, very hypnotic. And this is what happens when you train a GRUV unit on top of it. Very cathartic. Anyway, whoa, okay. Anyway, the next big advancement was in 2016, late 2016, WaveNets. So DeepMind, which we're going to talk about a whole lot in 2 weeks because we're going to talk about reinforcement learning, but one of the things that they did first that was really cool was they generated a deep convolutional network that was able to synthesize audio. And they did so in a way that really, really worked for the first time. I think this was really the first time any of this ever worked really well. Are you listening to this recording? Right, there's some recordings here. So what's going on here is that instead of using an RNN, they're actually using a convolutional network that's used autoregressively. So what does that mean? Is that the network it analyzes audio at the sample level, and it uses these what are called dilated convolutions to kind of, because okay, remember this may not be worth getting into right now, but remember like this idea that in convolutional networks you have this sort of notion of a receptive field. So the original input, a convolution, like a convolutional kernel that extracts features from it, is working at this one spatial level. But then the next layer, that activation is then picked up by a new convolutional filter, which is bigger, and so it is a function of an expanded field of pixels, right? Now this doesn't scale that much. It just scales up by like 1 or 2 pixels per layer, so that at the end your receptive field, that like one of the high layers the high layer convolutions are a function of, is okay, like maybe it's half the size of the image, or maybe it's the whole image, but it's still not that big. Audio, to make audio have any sort of long-term coherence, you have to go across thousands of samples. So the way that they actually achieve this is by doing these sort of skip convolutions, and you can kind of see that in this visual. So what they do is like, okay, in the first layer, you the receptive, like the convolutions, the kernels are actually operating on adjacent samples, but then in the next one it skips by a factor, it skips by an amount that is multiplied by 2 at every layer. And so if you do this over many layers, you expand the field, like by the receptive field, by doubling it at each layer basically. And at the end you actually have a function of many samples. And it turns out this works pretty well. I know that's like a very hand-wavy explanation, but it'll make sense that if you read the blog post at least. In any case, then what you do is you use the network to predict the next sample of audio, and then you do it again. It's autoregressive, which means that like you use it once to predict the next sample, and then that next sample becomes part of the input. So, which actually is kind of a disadvantage because it makes it slow, but it does produce really good audio, as you can hear. It still sort of feels like it doesn't have very good long-term coherence. You know, the music is sort of like, you know, jostling around. Actually, we can go here and check out some of the other samples. So you read the blog post, it's quite lucid. And they first showed how it sounds like compared to previous methods, right? So this is like an old school way of doing voice synthesis.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
Concatenative synthesis.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
And WaveNet.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
It doesn't sound that much better, but the point is that the main point, because we've really optimized vocals, right? But the point is that you have a physical model of vocals, but you don't have a physical model of jazz music, right? That's like, because that's really complicated. There's like all these instruments in it, you know. So the fact that you can just take hundreds of hours of jazz recordings, and yeah, I think this is, let's see, making music. Give it hundreds of hours of jazz recordings, and then it could produce what sounds like jazz piano. You know, talk about the ghost in the shell, right? Like, you know. So, there's some neat things that they do here. Okay, so check this out. So the WaveNet is like other generative models. It can be conditioned on labels, and it has to be conditioned on labels if you want it to generate speech, right? Because you have to provide a label that says what word you want it to say. Technically, it operates at the syllable level, so what syllable to say. And so, what if you don't condition it? You just give it thousands of hours of vocals, but you don't give it any labels, and then you just ask it to produce vocals. So like, what is it going to sound like? So this is what random English sounds like. You think that's what English sounds like to someone who can't speak it?
But English from the UK.
That might be UK English, yeah. Yeah, it was UK English.
Yeah, it does sound like UK.
Yeah.
UK German.
I thought they did this for Chinese too, but I can't remember. They definitely produced Chinese that was, yeah. Okay, so here's some Chinese. I don't know if they did the thing where they just had it make babble Chinese. No, I think they just did it for English. So I thought actually it would be really funny to, oh, where did I put that? Yeah, it'd be really funny to try to do the automatic closed captioning, So I put this online.
I just enabled those verses. There's more to it. I can't determine the name because I just over it. It's very to be the nota that I feel on.
Natuurlijk de signalen afspreken, zo afzet. Ziet zelfs bij huis.
Anyway, I like to check back on this every few months because YouTube is constantly upgrading its automatic captioning algorithms, and so it actually changes the captions once in a while. It is a little funny joke. When WaveNets came out, they were prohibitively difficult to train, and actually there was no details about its architecture. Very quickly, an open source repository popped up in TensorFlow, which I actually worked on a little bit. Like the main author of this repository got plucked by DeepMind after he started working on it, so then he started working there. And so this is an open source implementation of WaveNet. You can throw in just basically says, okay, give it a folder of wave files, and it will learn a generative model that will synthesize more audio like it. Ideally, you give it stuff that's relatively homogeneous. So like, it'll learn pretty well like the less variety of the sound that you have. It'll learn like a timbre pretty decently. It's very difficult to give it like very homogeneous music, or heterogeneous music. So like for example, I actually tried to train it on opera. Like I gave it a whole opera, The Barber of Seville, and then if you all right, tell me you don't hear the fat lady singing, right? Like you hear that, like, and the tenors. There's a sort of tenors going on. Yeah. Anyway, so that's available to you if you're interested in messing around with WaveNets. You can definitely download it and start to play with it. I don't know if it's hard to replicate DeepMind's results because they used really large networks to train WaveNets. But it's something that you can kind of look into. And then actually more recently, so Sander Dilleman is actually, and I'm going to show some of his work in just a bit. Sander is a scientist at DeepMind, and he worked a lot in WaveNets, does a lot of stuff with generative models of audio. And this is just from, this is already 5 months ago or so, but 5 months ago they figured out that by, as you can see, stacking WaveNets, so just making bigger WaveNets, you're able to get even better long-range dependencies. Okay, so like listen to this. This is just from 5 months ago. So if you listen to it long enough, it does start to feel like it loses the melody here and there, but it feels like it's starting to become more and more coherent on a longer term basis. And it's amazing because it's completely unsupervised generation of audio. It's just generating music from scratch, right? Now keep this in mind because I'm going to show you some stuff. I'm going to show you some stuff in a couple of slides that is going to kind of speculate on what we can do with that ability, which will actually be a good way to close today. I wanted to also quickly show you guys some stuff by Magenta called NSynth. Again, like I don't have any demo to show you, but these are because I haven't really used it. But if you are interested in generating audio, Magenta in particular with their NSynth project has a lot of tools that you may find useful. How many people here are interested in audio? Okay, lots of you. I would definitely look at them first because they're kind of doing the most in this sort of subtopic right now. And NSynth is basically WaveNets that are conditioned on instruments, like musical instruments. And so, okay, like you can create physical models of neural models of bass and flute and whatever. And then because you have this sort of latent space that you've projected all these instruments into, you can combine the instruments. So you can make instruments that are like halfway between two instruments, like a bass plus a flute, or a flute plus an organ, and then they actually have software that lets you turn these into instruments that you can use, like actual like virtual or VSTs or whatever, or audio units. And then the NSynth Super is really cool. That basically embeds NSynth into this like handy dandy device that lets you generate audio like parametrically. This was made by the Creative Lab. So along this two-dimensional grid, you have 4 instruments in the corners, and then instruments in between them, right? So you can, and it's MIDI playable. That's lovely, huh? Unfortunately, it doesn't render fast enough to be able to do this in real time, so I think the samples are preloaded, but I think we're getting closer to being able to generate them on the fly. Also worth noting, this is already kind of old, so there's probably more up-to-date stuff, but this is a really nice blog post from a couple of years ago on how to use recurrent neural networks on the symbolic level. So, of course, like, a lot of what's new is, with things like WaveNets, is generating audio from scratch, like audio at the audio level, at the sample level. But we've been working with music at the symbolic level for a lot longer, and you can use, of course, a lot less sophisticated methods to work with MIDI because it's such a lower dimensional signal, and so you can use actually RNNs and LSTMs like really nicely to compose MIDI. So, let's say you can download a data set of, thousands of MIDI tracks and then synthesize new MIDI, which MIDI, of course, you don't hear it, right? MIDI then has to be played by some, go through some synthesizer. So like, okay, so here's some examples of it generating like reasonable melodies. Pretty good. So yeah, if you want to get information on that, I would definitely encourage you to look up. Even though it's pretty old now, I think this is actually a really good place to start.
Also,
yeah.
They released just like 2 days ago this thing called Magenta Studio.
Oh, really?
Which lets you do some of that stuff just on install on applications.
Oh.
As plugins.
I'm unaware of that. Magenta Studio.
Yeah.
This probably won't work. Magenta, yeah.
It's just it's the regular Magenta website /studio.
Okay, cool.
So they continue, and some of the DA stuff I think is also the generative part. It's all written in Node and JavaScript.
Oh, that's
so
really.
Electronics.
Oh, I got you. Okay. Yeah, this is definitely, like, I don't know much about, I can't say very much about it because I don't know about it, but like, it looks like, yeah, again, Magenta is a really good place to go. They have other stuff too besides for music stuff, but yeah, a lot of good stuff from musicians. This is cool. This is generating jazz chord progressions. This guy, Kunwo Choi. So yeah, you can get these like the so-called real book, which is like a whole bunch of jazz standards, and so basically learning chord progressions from these. So these are fake jazz standards. Not bad, right? So also cool stuff. I showed you this, I think, during the CycleGAN section, but like also worth, just because we're on the subject of MIDI, so you can use CycleGAN to like take MIDI and then turn it into a different style. So that's really neat. Definitely like another cool thing to look out for. Oh, and then this is, did I show you this last week maybe? I can't remember if we looked at this. Piano Genie, another Magenta thing.
We looked at it a few weeks ago.
Oh, we did? Yeah? Okay, so this is the thing where they basically, this is very similar, actually, the method they use is very similar to SketchRNN. I guess we might have covered this when we talked about RNNs. But basically, like, just if we, in case we didn't, I think we showed this, right? Basically, you have this small controller. Did we see this? Yeah? Okay. So you have this small controller, and then it maps a very low dimensional signal to a very high dimensional signal, right? And it's very similar to this process of like in SketchRNN, you have this LSTM encoder and decoder, which is able to map complex melodies into low dimensional feature vectors, and vice versa.
Similar to SketchRNN?
It's actually quite similar to SketchRNN, yeah. Anyway, Piano Genie I think is really cool, and you know, all the software's online. You'll start seeing this name a lot, Sander Tillemann, because he's doing a lot of really awesome audio stuff at DeepMind. Also, like, why did I bring this up? Oh yeah, right. Okay, so like remember that I already mentioned this, but of course with generative models, you can either do an unsupervised training, or you can condition them on labels. You know, so like if you provide a label, then your generative model can learn like discrete categories of objects. And so this is important for doing like vocal synthesis, right? So you have to be able to model vocals. And so, vocals are of course like conditioned on syllables and phonemes and words and things like that. And so, that's just a big standard for vocal stuff. Lyrebird, I think I showed you this before also. So like Lyrebird is a company that is working on more or less stealing people's voices. They have a demo that last time I checked it was actually not working anymore. But if the demo is still working, you're able to record a bunch of statements into the microphone, and then it learns a generative model of your voice, and then you can use it to synthesize things with your voice. So this is my voice being stolen by Lyrebird. Oh no, that's not my voice. That's.
Are you speaking about this in album?
Yeah. This is my voice.
Oak is strong and also gives shade. The pipe began to rust while new. Thieves who rob friends deserve jail. The right taste of cheese improves with age. Cats and dogs each hate the other. Move the vat over the hot fire. The hog crawled under the high fence. Act on these orders with
great speed.
Focus.
And also just worth mentioning along the same lines, this thing was released by NVIDIA called WaveGlow, and they have a pre-trained model. So if you want to do some vocal synthesis, like neural vocal synthesis, this might be a good place to go as well. I haven't actually tried it myself, so I can't say very much about it, but it looks pretty fresh. WaveGlow. And then I also wanted to, this already like 2 years ago, so of course people often ask about this idea of musical style transfer. You know, because we've seen style transfer, like turning the Mona Lisa into Google Maps or whatever, but can you do audio style transfer? So can you take, you know, some like polka music and re-render it as hip hop? Like, wouldn't that be awesome? And it turns out this is really difficult. People are working on it. Maybe it's a little bit like, okay, like of course this technically is a form of musical style transfer, but it operates at the symbolic level, right, on the MIDI. So can you do it at the audio level? And one kind of cute attempt at it was done by these guys, Dmitry Ulyanov, Vadim Lebedev, and basically they tried to apply more or less like style transfer, like except on spectrograms. And so okay, so here's the content, style, and the style transfer. So here's the content. Here's the style. And here's the content in the sound in the style of the style. Alright, a more complicated example. Oh, let's here's and the style.
7 years ago.
our fathers brought forth on this continent a new
So it's a cute attempt at it. I think this will get a lot better in the coming years, but and they have other examples too. Like, okay, I don't know. Oh, well, okay. That's not so bad. All it's really doing is like spectral like it's like just superimposing the spectrum on top of the content. Okay. Anyway, okay. So this is the last thing I want to tell you about, and actually, like, this is the craziest thing that I'll show you of this entire class, I think. No, sorry, that's maybe a lie. But I really like to propose this sort of. This is a little section I've given in a couple of talks about audio stuff before. And it usually is one of the things that inspires the most, sort of like, okay. Like, I'm basically going to show you some different work, also by Sander Dillerman, and then connect it to some other stuff, and then speculate on what it means. So, as I mentioned before, most music recommendation is done using collaborative filtering, where you do you compare listener profiles, and you recommend music based on, the commonality of your tastes, right? And this is suboptimal for a number of reasons. Number one is that it requires having like listener data. So if you have some new artist that no one's ever heard before, no software is going to recommend them to anybody because there's nobody's listening to them yet. So there's a cold start problem. Now this would be solved if you could predict whether someone's going to like a piece of music strictly from the audio itself, because then you could process it automatically and then be able to predict. Now it turns out this is very, very difficult for many, many reasons. One is that the audio processing itself is very difficult to get meaningful information from, and also because of social factors. Like, it turns out that a lot of the reasons why we like music is not necessarily in the content itself. It might have to do with where the band is from. It might have to do with how we were feeling on a certain particular day when we listen to the music. It's like very, very almost accidental how we end up liking different bands. And so it turns out to be difficult. However, lots of people are still interested in this problem. And Sander, when he was doing an internship at Spotify about 4 or 5 years ago, and basically, they have tons and tons of audio, and they have tons and tons of listener data. And so he thought, maybe we can figure out a way to do content-based music recommendation. And so the approach that he took was the following. The idea is you have a population of users, and you have a population. Oh, I'm glad my mouse is back. I really need it for this. And you have a population of like records, albums, songs, whatever. And the goal is to project both of them into the same latent space. So you project all of the audio into the latent space, so they go here, and you project and then you could say, okay, two songs that are in a similar have a similar embedding in the space are similar to each other, right? This is very similar to word vectors and all the other embeddings that we looked at, and these two songs are very dissimilar. And then the idea is that you project the users into the same space, and the idea is that that's good recommendations because the user lies close to this music. And these are bad recommendations, right? Okay, so first, so you want this. This is what the goal is, because once you have that, you can infer that a user in the same part of the latent space as these songs is likely to like those songs. So how do you actually do this from the audio, right? So the idea is that you want to train a regression model which maps the audio signal to that latent space. So it's a regression problem that goes directly from the audio to this encoding. And and I know this is obviously like a very high level overview of this, but you can read all about this in much more detail here. But basically, it's a model that tries to simultaneously map the audio to the latent space and the users to the latent space using the following assumption. That users who listen, you can correlate the users with the audio, right? Because users are listening to certain songs, you have their audio, and so you can actually you can actually conceptualize this problem as a giant matrix multiplication of these latent factors that you're trying to learn times the actual songs gives you this user song latent embedding. Anyway, the point is that they tried to do this and they got some decent results. So okay, if you give them some Daft Punk, using conventional methods, you would just get more Daft Punk recommendations, right? Because these collaborative filtering systems tend to be very repetitive. So they'll give you the same the same piece of music because they operate mostly on popularity. Whereas their approach actually would get a lot of stuff that wasn't necessarily as well known, but might sound very similar, right? And it turns out if you try to evaluate it, it doesn't work quite as well at recommendation as like other approaches, but at least it has these. But maybe in the future it will. And so like right now, collaborative filtering is still kind of more successful at recommending music, but this has some promise. Yeah.
Do they consider using something that's more linguistic based? So training a neural network to recognize just like to actually describe music using things like upbeat, happy, blah blah blah.
You can do that, but what is your input source? Is it tags?
Yeah, existing tags, and then using that to apply that to songs that haven't been tagged, but then to generate new ones, and then using that and analyzing users.
Yeah, I mean, usually, like, okay, so people are interested in predicting tags, because then you could do, playlisting based on tags, let's say. But if you're gonna, like, one of the principles in deep learning that's very popular is that you train end to end. So whatever it is that you're trying to, like, you don't want to make one neural network, train that, and then have that input into another neural network and train that separately. You want to train them together because then it just works better. So if ultimately you're interested in music recommendation, you should just train directly from the input that you want to use to the recommendation, unless you're interested in tag word inferral because you need it for its own sake.
But this would be like a half measure.
Kind of, yeah, sure. Mm-hmm. So they did these t-SNE maps showing like clusters of artists that are related to each other. Okay, so you see like Prince and the New Power Generation, Eminem, Dina Ray, a lot of like hip hop and soul and funk here. Then there's another cluster. Oh, I had some other images that have other clusters, but you see that the music clusters together like pretty decently. And okay, so now here's where things get kind of interesting. Sander wrote about how in the process of applying, he uses convolutional neural networks for everything. And so he's using a convolutional neural network that takes in the audio as its input, and it outputs these embeddings for the songs. And if you analyze the network layer by layer, it has to learn features, right? Just like with the convolutional neural network, it learns image features. But this audio neural network learns audio features. And of course, like audio, that means that just analogize this to what we were doing with visuals, right? It learns audio features, and maybe at the early layers they might be very simple. It might be like sounds that are very squealish or something like that, or maybe sounds that are very harmonic or whatever. Those might be your simple features, and then at the later layers you might have much more complicated features, like for example, chord intervals, or maybe the identification of instruments. So you might have a feature that looks for guitars, or it might have a feature that looks for, tenor voices, or a feature that looks for meditative stuff, or things with bells. Like very high level features, and many of them, hundreds or thousands of them. And so this network is capable of synthesizing extracting those features for any piece of audio for the purpose of projecting it into this latent space. Now, so now here's where I'm going to propose to you something interesting. And this is what I call the iPod of the future. So you have this approach to doing content-based audio feature extraction, right? And the features might be kind of random in the example that we found. By the way, I should mention, just as an aside, in that blog post, Sander actually uses like basically the same sort of almost like deep dream approach where you, not deep dream, but visualization approach where you input lots and lots of audio and then find pieces of audio that maximally activate some of the features. And so you'll find like, and then he'll make playlists based on that. So there's like a playlist which is all of the songs which maximally activated a particular feature, and then you listen to them and try to interpret them, and you'll be like, oh, this one sounds like it's listening for 2 vocal harmonies that are separated by a major third. Something like that, right? It's pretty random. Sometimes, oh, and then it can actually, it had one that was able to identify what sounded like Chinese music, or like Chinese vocals. And so it's like, and it's completely unsupervised, right? You don't actually have any signal that says this is Chinese or not, but it's able to actually find features that are meaningful. So that's all interesting stuff in the blog post. But anyway, getting back to this. So imagine that you can do this kind of feature extraction, and the feature extraction is trained to a particular task, right? So what if you basically hook up these two things to each other, right? You have this regression model that maps audio into a latent space, and the audio itself is actually being generated by a generative model, right? It's not recordings. It's actually a generative model. It's your WaveNet, right? Now you have a pipeline for training a musical synthesizer to any arbitrary objective, any objective that you can do. So like, if you want to, for example, train a WaveNet to optimally make music that you yourself will listen to or will enjoy, you have basically all of the components to do that. If you tried to do it now, it wouldn't work very well, but in principle, it might work well in the future. And so, like, well, maybe, like, I don't know. It's a really hard problem to solve, but it seems to be kind of plausible that you may someday be able to make music that we may be able to synthesize music that is optimal for a person at a particular time. Like maybe the music that your iPod will generate for you is actually going to be like better than any music that you would want to listen to, maybe. Or even better, like maybe you can condition it on your like current biometrics. Right, remember this stuff with like the dreaming and imagination stuff. Like maybe you have like like a brainwave sensor or whatever that's like measuring your mood and your current sentiments. Maybe it's looking at your social media too to see what's going on in your life right now, and then it basically generates music that's optimized for you at that particular moment, depending on how you're feeling. And it's doing it like on the spot, and it's generating that one song at that one time. Like maybe it'll never play it again either. Like so basically, like eventually maybe like we're basically building like the matrix for music. So it's just gonna be just generating music that's optimized to a particular scenario at a particular time. This is the sort of like what I call the music maker's dystopia. Because where does that leave musicians? Of course, like, well, it's unclear. Obviously, like, but, this is a joke. No. So people ask me, like I've gotten in trouble with musicians for suggesting this kind of stuff, like, how dare you? But it's actually, this is really not true, because one of the things that's happening now, and Jan LeCun likes to point this out, is that in the more and more we automate things, the more we begin as a species to place value on things that are made by humans. So mass-produced things are extremely cheap. You go on Amazon and look for like handcrafted goods, they're obviously very expensive. And so that we attach more value to things made by humans. So I think as long as that's true, I think there's going to be like there'll still be a reason to be a musician, right? Because there's something very human about making music. And so I want to pull back in this dystopian scenario before I get in trouble with the other musicians in here. And also like to be more like, okay, that, like what does this mean for the studio of the future? Maybe you're going to have like really cool new tools that you could do, musical style transfer, or get recommendations of audio snippets you can use from your collection, or you can visualize, or there's all kinds of stuff that this will mean for musicians. That doesn't just mean unemployment. So yeah, iPod of the future. Yeah. Okay, that was the last slide. So just to recap, we did a lot of music stuff today. We looked at Glow. We looked at BIGGANs. Next week we're going to do not next week, in 2 weeks after Thanksgiving, we're going to do a mega lecture on natural language processing and reinforcement learning. I can't cut out both either one of these. Actually, it's possible that what might happen is one might spill into even week 11 because we still have time then, which is somewhat unplanned. I've got some other stuff planned already, but probably not for the entire 2.5 hours. So we won't shortchange these. We're gonna actually look at a lot of stuff, and I still need to prepare some of the NLP stuff. So it's actually kind of a work in progress. I really love talking about reinforcement learning because this is what we might consider the pinnacle of AI. This is the creation of artificial intelligent agents that operate in the real world and have an influence on the real world and interact with us and all this kind of stuff. And it's really, really the summit of AI today is reinforcement learning and AGI stuff. So we're going to look at lots of video game stuff. Of course, that's going to be very popular here. And NLP. So yeah, that's it for today. Are there any questions on the materials? Yeah.
Do you have any existing notebooks or in for guys? Is there anything about reinforcement learning?
Yes, there's 2 notebooks on Q learning and deep Q networks, which we'll talk about in 2 weeks. Those notebooks need to be renovated because I think Francis wrote them 3 years ago. So they might, I think they've been updated for the latest Keras, but I might be wrong. They're probably, I would say, not the most current place to get that stuff. I would look, if you really want to do some Q learning stuff, Q learning is kind of the entry point. I would try to find some Keras Q learning stuff. Or email me. I can share some links that I'll also show in 2 weeks. But if you want to get them in advance, just email me. Any other questions? I'll be doing office hours tomorrow, same time. I have a very late flight tomorrow, so I'll probably leave a little bit early. But let's say just email me either tonight or tomorrow morning if you want to meet tomorrow sometime let's say afternoon. Yeah, is there anything else? Okay, cool. So have a happy Thanksgiving if I don't see you at office hours, and I'll talk to you guys soon. Ciao.